Let's, let's get started. Welcome to the West Coast special edition of the COMSOC video seminar. We may have some new participants this week, so let me review the rules of engagement. Please keep your mic off during the talk. If you have a question, it's a good idea to type question in capitals in the chat box, and we'll be looking through the chat box during the question period to make sure we don't miss any of the questions. The talk will be 20 minutes. Then there's 10 minutes for a coffee break, and in that coffee break, there'll be some breakout rooms. If you decide to join a breakout room, you'll be randomly paired with somewhere between 4 and 8 people, I think is the rough number. And then you'll be reminded to come back for the second talk. Okay, so our speakers today are Francis Su and Matt Jackson. Francis is the Benedictine Carwa Professor of Mathematics at Harvey Mudd College. He's probably best known in our community for his use of extended versions of combinatorial lemmas, such as Sperner's lemma, to prove results in fair division. He served as president of the Mathematical Association of America from 2015 to 2017. Of course, I'm only hitting a few points here. And he has a new book in 2020. It's intended for the general public, called Mathematics for Human Flourishing. Today, he'll speak on multi-labeled versions of Sperner's and Fan's lemmas and applications. This is joint work with Frédéric Meunier.
Thanks a lot. Thanks for having me. It's nice to be able to join you guys, and thanks for moving the time for today. I'd like to tell you about work, as Bill mentioned, with Frédéric Meunier at École de Pont in Paris. This is work that we started together at the Math Sciences Research Institute in 2017, when there was a special year on geometric and topological combinatorics. So I should say a little bit of what I mean by topological combinatorics, but it's basically combinatorial questions that are motivated by topology. And today we'll see Sperner's lemma in the large. And you should know that it's equivalent to the Brouwer fixed point theorem in topology, which many of you may be familiar with. Cake cutting plays a big role. You may be familiar with the general cake cutting theorem, the NB-free cake cutting theorem due to Stromquist and Woodall, which basically says if you have a bunch of players with absolutely continuous measures, then there exists a division of the cake into n pieces and an assignment of players to pieces that makes everybody NB free. Some newer fair division theorems, which I want to tell you a little bit about today, are this version, which some of you may not be familiar with. So this is a version of cake cutting where you can divide the cake into n parts so that So suppose you have n-1 players and you have some other nth player who hasn't shown up in the room yet. You can divide the cake into n parts now so that when that last person comes, no matter which piece they pick, the rest of the pieces can be assigned. They can all be assigned in an NB-free way, right? The last person gets the first choice, and then the other n-1 players, the claim is there's still an NB-free assignment available to them. The theorem that I'm about to tell you today, that a multi-labeled version of Sperner's lemma will prove this result, although it's already been known earlier. One of the things that's kind of nifty from the result I'm about to tell you today is that there's a dual version, which was a little unexpected for us. And so the dual version basically reverses the role of players and pieces. And so in this version, which I'll tell you about, we like to call it the survivor style cake cutting theorem. And so this is a version where if you have n players, you can divide it into n-1 parts so that no matter who is voted off the island tonight, there still remains an NB-free assignment later. I don't know if Survivor is popular in your country, but it's a show where basically every night somebody gets booted off the island. And so the claim is you can always divide the cake into n-1 pieces so that no matter who gets voted off, there's still an NB-free assignment. All right, so how can we prove these theorems? I want to tell you about, I first should review Sperner's lemma, which is a statement about labeled triangulations of a large simplex. Here, if you imagine labeling the corner vertices 1, 2, 3, and then every vertex on the edge gets labeled by 2 or 3, because it is because the main vertices have those labels. You're allowed any labels on a face can be only one of the labels of the main vertices that span that face. So in general, if this were a larger dimensional simplex, the rule is analogous. And so here's a Spurner labeled triangulation. And what Spurner's lemma says is that there must be, in fact, a 1, 2, 3 triangle in here. You'll see at least one here. And the claim is, in fact, there's an odd number of little 1, 2, 3 triangles. Okay? This is a general theorem in n dimensions, n-dimensional simplex with n+1 labels, labeled in a Spurner fashion, should have a small subsimplex that is got all the labels. As I mentioned, it's equivalent to Barrow-Fixed point theorem, and actually combinatorial proofs of Spurner's lemma provide some of the simplest and easiest ways to prove the Barrow-Fixed point theorem. I'm not going to go over the bazillion different proofs, but I just want to note that there are, in fact, path-following proofs, which are constructive, meaning you don't have to just, you don't have to exhaustively search through all the simplices. You can actually find them in a way that has to do with following labels until you find a simplex that has all the labels present. One proof of this that I do want to highlight is the topological proof of Spurner's lemma, which basically says if you're given a triangulation and you imagine mapping this triangle to a triangle with vertices labeled 1, 2, and 3, and labeling and mapping every vertex labeled 1 to the corner labeled 1, all the 2's to the corner labeled 2, all the 3's to the corner labeled 3, then this defines a piecewise linear mapping of this triangle to this triangle. And a topological fact is that because of the labeling of Spurner's lemma, so imagine this being a big sheet of plastic wrap. And imagine this being a triangular dish. And you are taking this plastic wrap and wrapping it on this dish according to the way that I described. Then what you notice is because of the Spurner labeling, the 1, 3 edge here gets wrapped onto the 1, 3 edge here. And the 2, 3 edge here gets mapped on the 2, 3 edge here, etc. And what you see is because of the Spurner labeling, the plastic wrap gets wrapped around the edge once. And the topological fact is that if the boundary gets mapped once, then the interior actually has to get covered. Your dish actually ends up getting covered by the saran wrap. And so an easy proof now is that if you just look at the inverse image of any point in the middle of the saran wrap, it has to have a pre-image over here somewhere. In fact, it has to have an odd number of them. And that's why there are 3 of them. Okay, if you keep that in mind, then you'll be able to follow the next, the things I'm about to say next. So the basic idea of using these kinds of lemmas to solve fair division problems is to look at the space of divisions as a topological space. You break it into pieces, you label the vertices by the preferences expressed by players, and then you use those labels to find a good solution, and you might home in on a solution that way. I'm going to show you a very quick application to cake cutting due to Simmons in 1980. Here you have a space of cake divisions parameterized just by the widths of the pieces, and that's a point in a simplex. Every point in this simplex is a division of cake. The corners correspond to one piece having all the mass. And so if you just label, if you imagine triangulating this and labeling every point by, let's say, Bill's preferences, then the claim is because of, if Bill is hungry, at the corner he's going to demand here piece 1, here he's going to demand piece 3. And all along this edge, piece 2 will be empty, so he's going to demand 1 or 3. And so if you imagine doing the triangulation this way, you get a Spurner labeling, and that produces a 1, 2, 3 triangle of some sort. And if we're just using Bill's preferences, that's a point of indifference for Bill. But you can get all the players involved if you assign owners to every vertex so that they're different people, Alice, Bill, and Charlie. And then a 1, 2, 3 triangle corresponds to an assignment of different pieces to different players for 3 very nearby divisions. And if you do this for finer and finer triangulations, what you're going to get is a point that is the convergent, it's the limit of a bunch of subsequence of 1, 2, 3 triangles with NB-free assignments. So that's the NB-free point if you want to find it, and you get an approximate NB-free division just by stopping the algorithm any point you like. Okay. So a theorem that I proved with a few collaborators in 2002 is something called the polytopal Sperner Lemma, which asks for polyhedra, that's what a polytope is, labeled in a Spurner way. Let's say 1, 4, this edge only has 1s and 4s, and this 1, 4, 9 facet only allows labels 1, 4, and 9. What can you say about the existence of anything? And the claim is if you look for simplices that have all different labels, we'll call those fully labeled cells, then there must be a certain number of them. This was a question about Tanasov, and we proved that if you have an n vertex d-dimensional polytope, polyhedron, with a Spurner labeling, it has to have a certain number of full cells, n minus d of them. For a simplex, this becomes d plus 1 minus d, which is 1. Okay? The picture here is a picture of a polygon, a pentagon, labeled in a Spurner way. You can see along the edges it has the Spurner labeling. There are, in fact, 3 full cells here, A, B, and C. They're marked in this picture. The other shaded cells are I'm just suggesting for you a path following argument, which I'm not going to talk about. If you want to ask me questions about that later, I'll tell you that. But I want to show you another proof, which is a topological proof, which is, hey, map this to another pentagon such that every vertex labeled 2 is mapped to the corner 2. And if you imagine then the saran wrap covering this dish must cover the interior, then one way to see why there must be some full cells inside is that the interior has to get covered in some way. In this case, it gets covered by 3 triangles, and these 3 triangles appear as full cells in the pre-images. Okay? This is an important idea, this picture. Keep this in mind now for what's to follow. Okay, so what's the multi-labeled Sperner lemma? This was conjectured by my collaborator, Frédéric Meunier. It involves a Spurner labeling where you have 2 different people with 2 different Spurner labelings. So we have a red person and a blue person with Spurner labelings. And the question that he asked was, what can you say about the interaction between these labelings? And the claim is, in fact, you can say something, and this actually has some consequences for people like us who think about social choice. So for instance, if I take the number 4 and I split it into 2 parts, in partitions, 1 and 3, or 2 and 2, 3 and 1, you give me some partition of this into 2 parts, then the claim is there must be a triangle that realizes this partition using a specified number of labels. So I claim, for instance, that there is a simplex, it's the red one here, where the first player, the first labeling, uses at least 1 label, and the second person uses at least 3 labels. So that's, of course, here you can see in red, it's 1, 2, 3, they're using 3 labels, okay? But it works for any partition. So if you ask me to find a 2 plus 2 division, then there are purple triangles here where the one player uses 2 labels and the other player uses 2 labels, okay? This number 4 is not an accident. It's actually n plus n minus 1. So if you take any division of m plus n minus 1 into m pieces, there's a simplex for each I such that the ith labeling uses that division of that many labels, at least that many labels. And then the dual version is for any division of m plus n minus 1 into n parts, then there's a simplex where for each label, it's used in a certain number of labelings, okay? And so just to give you an example, this is our main theorem. You can see here in the other direction to think about is looking for labels used by a specified number of labelings. So again, this triangle, actually, red triangle, actually is the first label's used in one labeling, the second one's used in two, and the third label is used in one labeling, at least one labeling, okay? So this may seem like, whoa, okay, you've sort of just gone crazy with this. I don't see what the point of this is. Well, the point for us is that each of these Spurner labelings is actually somebody's preference, right? One could be Bill's and one could be Matt's, for instance, okay? And so how do you prove this? The way you prove this is you think about, it turns out to be based on the polytopal Sperner Lemma. I could think about a big polytope, which is a product of a simplex of dimension m-1 and n-1. So the corners are labeled by m people and m labels. And I'm just showing you the simple case where you just have two labelings, just like the picture in the previous slide. Blue, so basically we're going to map a prism to itself so that the top side, the red side, follows the Spurner red labeling, and the bottom side follows the Spurner blue labeling. You can convince yourself this is actually a polytopal Spurner map in some sense, because the corners, corners get mapped to the corners and the sides gets mapped to the right sides and things like that. So then by the polytopal Sperner lemma, there actually has to be, this saran wrap that's now three-dimensional has to get covered in some way. And so now the question is, why can you find these various kinds of Spurner labelings, these special simplices of various types? And what's interesting is, it turns out that if you just look at inverse images of various points, it actually reveals something, okay? So for instance, if I take a point here, this, because it gets covered, the claim is any simplex over here spanned by the main vertices that covers this point, believe it or not, has to have two labels on the top and two labels on the bottom. That's a little surprising if you think about it geometrically, but it corresponds to the 2 + 2 situation we were looking at earlier. In fact, it gets better. If you take this special point, this was a surprise to us, you could find a point such that no matter which simplex contains this single point, any simplex that contains this single point here must contain all three vertices at top and one of the vertices on the bottom. Excuse me. And once we realize that, then in fact, the dual versions also reveal something. If I look at these points, any simplex that contains this point that's over here to the right must actually contain two vertices, one red, one blue on this corner, and at least one of the simplices on these corners, okay? And then it turns out the barycenter plays a very special role, and this is the NV-free part. The inverse image of this point, actually, you're able to do this funny thing where you assign owners to labels, Alice, Betty, Charlie, and get an NV-free assignment, and that turns out to be critical. So that actually reveals all these different kinds of, the existence of all these different kinds of simplices. And I'll just finish now by pointing out that you can talk about a dual version, which is dividing rent among roommates. It turns out to yield a dual Sperner lemma. And there are analogous survivor and secretive roommate theorems where you can have people enter late or leave before the division's made. And then I'll just finish by saying there's actually, we sort of took this one step further to something called Fan's lemma, which is a combinatorial equivalent of something known as the Borsuk-Ulam theorem, which some of you may know is actually equivalent to the ham sandwich theorem. So it's a division theorem. And so we're able to actually generalize this in a very analogous way. And I don't have time, I think time is running out here. So I'm just gonna wave my hands a little bit and just show you. Basically, Fan's lemma asserts the existence of certain kinds of simplices that have an alternating pattern in their labels. And you can have different number of labels than the dimension of this sphere, which is a triangulated sphere. And it yields a certain kind of what we call a multi-fan lemma with a certain division of partition of the letter D, which is the dimension of this triangulated sphere. And it leads to a certain kind of division theorem, which is says if you take n minus 1 and you divide it into m parts, that there's a way of assigning these pieces to two portions so that if you have so this is a division of people into groups, and what's going to be the case then is each group is going to believe that these portions are either exactly half, or within each group you'll be able to find a certain specified number of people who agree on how undivided they are. Okay, I'll finish there. If you're interested in seeing one of these algorithms in practice, the New York Times actually did a version of the Sperner Lemma thing from one of my papers. And if you just Google divide your rent fairly New York Times, you'll be able to find it. It actually is implementing a version of Sperner's Lemma. And I'll end there. Thank you very much.
Very nice, everyone. Let's turn off our mics temporarily and give a hand to Francis.
All right, that's the timer.
I'm looking in the chat window and I don't see any actual questions. I do see, I see a question from Nidhi Rati. Nidhi, did you want to ask your question? It's kind of a question, yeah. You'll have to unmute.
Yeah. Hi. Great result. I would like to ask if there is like corresponding generalization of this Sperner's lemma which you presented to KKM lemma as well, which is the covering equivalent of Brouwer's and Sperner's lemma.
Correct. Yeah, that's a great question. Yeah, so for the polytopal Spurner lemma, if you look in the paper, we have a KKM version of that, which is it's exactly what you'd expect. Okay, so there's no surprises there. I don't believe in our paper that we talked about it's been a while since I've looked at the paper. I don't think we talked about a KKM version, but I suspect that there is one. But maybe that would be a wonderful thing to think about. For those of you who don't know, that the KKM lemma is well, I guess this is an econ audience mostly, so you probably know what the KKM lemma is. It's a set covering lemma that is very similar to Sperner's lemma. It's a great question.
Okay. Thank you.
We have a question from Rita Laraki. Rita, you want to ask a question?
What about KKMS?
Yeah.
Great talk.
The Shapley, KKM Shapley.
KKM Shapley.
Yeah. Yeah. I don't know that we've worked out what this would look like for KKM Shapley, but it shouldn't be, it should, in fact, the multi-labeled version of the multi-labeled Spurner ought to yield an interesting way of proving KKM Shapley, right? So KKM Shapley, so if you look at my rental harmony paper, there's sort of a path to doing KKM Shapley through the rental harmony paper. So when you assign owners to vertices, and then choose a labeling such that every corner can have every owner, then you can use the method in the rental harmony paper, the method I just described here, to prove KKM Shapley. So I don't know that it requires, maybe you're asking for a generalization of polytopes. I'm not sure if you're asking that or what you're asking.
Just to know if there is any use of KKMS to have also some kind of fair division properties, strong properties, you know.
Yeah.
That was my question.
Well, if I recall KKM Shapley, KKMS, it should be used to, it can be used to prove a NB-free version of K-cutting.
Errol Siegel Halevi asks, do you have a physical model of wrapping a dish with a triangulated cloth?
Oh, do I have a physical model? I thought about looking in my kitchen and getting out some plastic wrap this morning, but are you thinking about something a little more involved?
No, something simple just to exemplify, because it's a very beautiful argument. I've never seen it before. It makes all this this topological proof much easier to understand. So I thought it would be nice to demonstrate it.
Yeah, and in fact, there are some really cool recent proofs of Sperner's lemma that sort of rely on this intuition. One that I'll point you to, and now of course I'm forgetting who did it, but there's a recent one from 2008 that appeared in an Econometrica article, which basically does the following. So let's see if I can remember this. So you have a Sperner labeled triangulation of a triangle. And what you do is you gradually move think about a dynamic process where you gradually move every vertex to the corner, the main vertex that it's labeled the same. So all the ones gradually move to one, all the twos gradually move to twos, etc. So you can think of this as saran wrap that's sort of just pushing the plastics to the appropriate corners, right? And the argument here, which is really nifty, is that if you look at the volume function, so if you look at the volume of these, the total volume of these triangles as you move them around, it's a polynomial function of time. You argue that for small bits of time, this function must be constant, and if it's polynomial, then it actually must be constant for all time. And so at the beginning, at the end, at the end of the process, there has to be one of these little triangles that has the same volume as the full thing, and so that's a 1, 2, 3 triangle. Yeah, so that's another version. That's another way of thinking about the saran wrap argument.
What is this paper? Do you know?
Yeah.
Okay, I see.
I can send it to you later. I'd have to look it up.
Okay, cool. Very cool. Thank you very much.
Francis, I had a question that might be a naive question. You pointed out that Sperner's lemma has a constructive proof where you follow paths. Presumably, when you apply it to a fixed point, you lose that constructive nature because the fixed point theorem, the existence of a limit point itself is non-constructive. Have you considered the possibility of looking at special cases of preferences in which you could carry the constructive argument over to the limit point?
Yeah. So this construction, the Sperner's lemma argument does yield an algorithm for converging to the fixed point, and so that was used in the 60s and 70s in a way that I haven't described here. But basically, it involves, in some ways, you can think of it as changing the mesh size as you go, and so in some sense, that proof is in fact constructive. And it's just constructed in a limit in some sense. And you can get bounds on how close that you are by running the algorithm long enough. And this was used, I think, in the 60s and 70s to do what are called homotopy algorithms for finding fixed points.
Are there other questions? Okay, let's thank Francis again.
Thanks for having me.
Turn off your... And I think we're going to move to the coffee break. That means you'll be invited to join a breakout room for 10 minutes. You can say yes, you can say no. And you'll be randomly paired with a small group of other people to chat. And then you'll get a rejoin message in about 10 minutes. Dominic, are people basically back, or should I wait a couple more minutes? They're back. Okay. Well, welcome to part two. Our second speaker today is Matt Jackson. Matt is the William D. Eberly Professor of Economics at Stanford. His research is in the area of game theory and microeconomics, but he's probably best known for his work in this group on social and economic networks. He's published 2 books on networks, one intended for researchers and one for the general public. And he served as president of the Game Theory Society from 2020 to 2022. Today, he'll speak to us on learning through the grapevine, the impact of noise, and the breadth and depth of social networks.
Great. Let me share my screen. Excellent. So people can see that?
Yes.
Wonderful. So this is a project that's joint with Suraj Maladi, a student here, and David McAdams at Duke. And we're looking at how people come to learn information and form opinions. And obviously this is a big issue in collective decision making. And I think, it's been in the press quite a bit recently. Here to do 2 quotes, one from Elizabeth Warren saying that she wants tech companies to start policing disinformation and misinformation. And then a response from Mark Zuckerberg saying that Facebook and internet platforms shouldn't be arbiters of the truth. And one perspective on this is that whatever group you have, if they're going to try and police information, they all have biases, and they're facing, especially platforms, huge volumes of information, and it's hard to figure out what is true. And if you look at some of the machine learning issues, they already have problems with satire, humor, and so forth. So for instance, some of the algorithms that have been put in to find disinformation come up with things like The Onion and other sites that are satirical ones as being spreaders of false information. And one question we could ask is, how can we ensure truth without policing content? And what we're going to do is look at a very simple model where people are learning from distant sources. And the first thing is that, learning with with noise, various forms of noise in the system is going to require hearing from exponentially many sources. And with some uncertainty about the relative biases of whether or not you're hearing things in one direction or another about some factual question, learning can be completely precluded. Limit learning, and I'll make that precise. And the main point that we'll make at the end is that trimming the depth or breadth of a network can improve its learning properties. And I don't know if you've been following, but WhatsApp and Facebook have both limited the number of people that somebody can forward a message to. So the putting caps on the breadth of this sharing can actually trim the tree in ways that can be effective. So the simple model is going to be that there's a state that's either 1 or 0, and there's a learner trying to learn that state. And they have a prior probability theta that the state is 1. And there's a bunch of initial senders who are going to get information about that state, and they're going to relay that to their friends, and they'll relay it and so forth. And eventually the receiver is going to hear signals via word of mouth. And along the way, there's 2 things that can be happening. One is that there's just mutations in transmission. So 0s can switch to 1s, 1s can switch to 0s. We'll have those probabilities be less than 1/2, but for simplicity reasons. IID probabilities on any particular message mutating. And you could think of these as being random, but they also could be deliberate. So it could be that there's some node that's saying, spreading false news. They always send 1s. So if a message comes in as a 0, it's going to mutate to a 1 from them. Or it could be just that there's a misinterpretation. And regardless of what those incentives are, what really matters is the fraction of time that 0s go to 1s and 1s go to 0s. So it's effectively just be a Markov chain. Also, you can have probabilities of passing information along depending on what it is. So you might have one probability of passing a 1 along. It's going to be dropped with the reciprocal probability. And similarly with 0s. So it could be that significant results get passed on with higher probability. Funnier jokes get put on, more salacious rumors, etc. For today's purposes, we'll just look at the case where they're going to be equal dropping. But there's actually interesting issues about the dropping rates, because you can infer something by saying, I haven't heard much about this, therefore I believe that the state must be 0. So you can actually update on how much volume you're hearing as well as the content, and we spend time in the paper looking at that. So what we're going to think of is some learner here, the blue dot. They've got a bunch of people out there in a network, and there's some state. Let's suppose that the state is 1. These top row of dots are going to be the initial people who do investigations or get information about the ones. And what's going to be happening is over time, these things are going to be mutating or being dropped. So some of the people actually discover the 1, some hears it as a 0, some doesn't hear anything. And then these get transmitted through a network eventually towards the learner. And so through this process of mutation and dropping, there's going to be a set of messages that are eventually heard by the learner, which could differ from the original state. And so obviously this is a Markov chain with the absorbing state of being dropped and various mutation rates. So what we're going to think of is that think of NT original sources that you're hearing of, these different chains of length T, and think of them as being independent. And as T grows, each chain is going to become less informative because of the possibility of noise building up along the way. But if NFT grows, you get larger numbers. And so what we're looking at is the trade-off between those. And the belief will model as what's the probability that the state is 1, given information from NFT IID chains. So as we let T go to infinity, how big does N have to be for my belief to converge? So we'll say that f of t is a threshold for learning if when n of t is relatively larger than f of t, then the belief probability goes to 1 or 0. So I'm going to learn perfectly what the state is if I have something of a higher order than f of t. But if I have something of a lower order than f of t, then my belief just goes to the prior. So let's say that's a learning threshold. And first lemma is that if we're looking at a positive probability of dropping and mutation rates less than a half, then the threshold for learning is just an inverse of p times 1 minus mu 1, 0 minus mu 0, 1 squared. So all of this raised to the tth power. So effectively what happens is the n of t needs to grow exponentially in t, based on what these error rates and dropping probabilities are. So you've got a race between figuring out what's the relative fraction of 1s and 0s that you should be hearing based on what this process looks like. And if you hear enough of these, then you're going to be able to learn, and otherwise you won't. Okay, so if paths are expansive enough, you learn, but it requires exponentially many sources. And short of that, you don't learn anything in this extreme case. The next point is that learning actually depends on knowing exactly what this mu1 and mu0, what the rates of mutations from 0 to 1s are and 1s to 0s. If they're not known exactly, then you're basically in the, when you think about any particular chain, over time, these things are going to mix so that the relative chance of seeing a 1 or a 0 is proportional to these relative rates. And all you're getting is a slight probability of difference based on what the starting state was. And the longer the chain becomes, the less information you have about that starting state, and the more you're getting just what those limits are. And if these aren't exactly known, then that uncertainty, even small amounts of it, completely dominate the information that you could get from the starting sources. So if that, say if the ratio of mu1, 0 to mu0, 1 is unknown with connected support, whatever that support is, then regardless of n of t, the limit as t grows of your belief is going to be the prior. So if you don't know exactly what those rates are, you're not going to be able to back anything out as a Bayesian learner. And so that means even small amounts of uncertainty about that relative bias and mutation rate preclude learning in the limit. Okay, so limit learning is fragile. You're learning from slight tilts of fractions of signals, and if you don't know what that tilt should be, you can't sort out the signal from the noise. So partial learning is what we end with. And so you can be learning from people who are near and far. And in your network, if information is originating from people close to you, it has fewer chances to mutate or be dropped along the way. And as it's coming from more distant sources, then you've got increased probabilities of having it mutate or be distorted. And so as you change the shape of the tree, you're changing the relative number of people at a great distance compared to people who are close. And that relative distance is what you can control by changing the relative depth and breadth of the tree. So if we cut the tree at a greater depth, then we're making sure that you're only getting messages that have fewer chances to mutate. If we cut it in terms of breadth, then we're going to be increasing the ratio of nearby to far away nodes. So as you increase the breadth, if you increase the degree in a network, you increase the relative number of nodes at a distance compared to ones that are close by. And so those are the two levers we'll be pulling. So again, let's think about this setting where the dropping probabilities are the same. Imagine that now I'm a learner, and these mutation rates can differ, and they're unknown, so I don't know how many people are right-wing extremists or left-wing extremists. They're going to be distorting messages, or how many people can't understand messages. And let's take it that the receiver has a symmetric prior over the state and these mutation rates. And in that case, what you'd like to do is, if you had full symmetry, you would just go with the majority of signals. So if the majority was 1, your best guess would be 1. If the majority was 0, your best guess would be 0. And so let's just do a quick example. Let's suppose that the dropping rate is 0.2. Sorry, the passing rate is 0.2. And then there's about a 0.03 chance that a 1 mutates to a 0 and a 0.1 chance that a 0 mutates to a 1. So the bias is going to be that most messages are going to tilt towards 1s instead of 0s. And if the true state is actually 1, that's not a problem because most of the messages will come through as 1s. So when you have a bias in one particular direction, it's the state that's disadvantaged that is going to be the harder one to learn. So if the true state is 0, then messages that travel too far are more likely to mutate into 1s. And in this case, with these numbers, once they've traveled 7.5 steps in the network, they're more likely to have switched to 1s than 0s. If they travel less than 7.5 steps, they're more likely to still be 0s than 1s. So 7.5 is the magic number for these particular parameters of how far things can travel before they're more likely to have flipped over to be false than to be true. So we worry about the veracity of these messages in the disadvantaged state, in this case, state 0. And so one thing we could do is just cap the tree at depth 7.5. So each message would be more likely to be true than false. And that would be one way then to ensure veracity of the messages, at least on average in expectation. But again, more distant messages are less likely to be true. And so maximizing the overall probability that at least half the messages are true can involve a lower cap than just the cap that ensures that any particular chain is more likely to be true than false. Because what we're worried about is this relative number of close by messages to far away messages. And so for this particular example, if you look at this tree depth, here we've got, if the breadth, if the average number of connections is just 1 that each person has, then it looks like just like a line. Then things are very flat in terms of what the tree depth looks like in terms of the probability of most signals being correct. If you start increasing the degree in the tree starts getting wider and wider, and you get more and more messages coming from further out in the tree. And then it becomes more important to actually cap the tree depth. And instead of just the 7.5, where any particular chain is more likely to be true than false, what you end up with is if you can cap it at a shorter distance, in this case, somewhere between 5 and 6, then you're better off in terms of having the highest probability that most of the signals that you're getting are going to be correct. Okay. So in this example, we're worrying about the veracity of messages in state 0. And I think one thing that's very important, and if you talk to people here on these platforms, one thing that they have a hard time doing is actually tracing the full path of a message. So seeing what people are forwarding and how far something's been forwarded, especially in something like WhatsApp, which is encrypted, that can be a hard problem for them. But it's much easier for them to see how many people somebody's actually passing a message to. So in cases where you cannot control the depth of a tree and you want to make sure that most information is true, you can still play with the breadth of the tree. And so you can track how many times people are forwarding something and limit that. And so if we go through the same example, here we've got different depths of the tree, and then you can see what's happening here in terms of, you know, limiting the breadth. And in this case, as the tree gets, so here when we see the 10, the fullest depth to the tree, then actually limiting the breadth makes sure that you're getting more nodes that are relatively close compared to far, and that increases the probability that most signals are correct. Now, if you have a tree that has very low depth, so for whatever reason things don't go very far, then then you can actually work with very high breadths and still get relatively good probabilities. But once you start having things travel greater distances, then you have problems, and it's better to actually start squeezing this breadth in. And in fact, here we're getting optima again in about the 5 range. So you can go through and do the calculations of where you want to cap messages in order to make sure that they're more likely to be true than false. And you can get a simple formula for that. So in this case, if we had those particular parameters, that's where we get the 7.5 from. That comes out from a simple calculation of just the mixing time on this Markov chain. And if you do breadth, if you can't control the overall depth of this, and you can only work with breadth to try and increase the relative frequency of close by messages to far ones, then effectively you can work out a cap on D, and here's a sufficient condition for a cap to ensure that the majority is more likely to be true than false. And it again works off the mixing properties of this Markov chain. And if you plug in the parameters that we had there, that cap turns out to be 4.6 if the depth is quite large. So effectively, that gives you one rationalization for the WhatsApp and Facebook kind of logic of capping things at 5, is that they're dealing with relatively non-trivial mutation rates. And in that case, then, capping that breadth, if they can't control depth, is going to be a good way to do it. So one further point you can go through and work out, if you have very different mutation rates and the learners are not aware of those mutation rates, so if they have a fairly symmetric prior and you have substantially different mutation rates and P is fairly large, then it's impossible for any depth or breadth calculation or limitation cap to actually ensure learning. So there are some cases where you're just stuck and there's nothing you can do. So in summary, we've got a situation where we've got lots of mutations, dropping by ascending, long chains. You're going to need lots of chains, and slight uncertainty about mutation kills learning, and you're sort of stuck then trying to improve the ratio of close by to far sources to improve the partial learning. And crude simple caps on passing can actually make learning possible when otherwise it would be precluded. So, I think thoughts of what we learned from this. In the abstract, there's a lot of work that's been done looking at learning in networks and consensus forming and so forth. And you get all these positive results that things will converge in the limit. It might take a while, but those are all without noise. And when there's substantial noise and unknown noise, then it's going to be much harder for people to work with, and actually controlling the tree might be our best way of improving learning without actually policing the content of messages. I think that's a good place to stop and take questions.
Okay, folks, let's unmute and give a round of applause to Matt. I was looking in the chat a moment ago and my chat just disappeared. I've lost my chat box. Alan Sang had a comment and Paolo Turini had a question, I believe.
So yeah,
And
so
Ariel had a question.
Alan, do you want to start or that's enough?
Yes, go ahead, break in the people I named for sure.
All right, so I'll start with my question then. So basically, so is the problem the fact that there is trees have large breadth or large depth, or the fact that agents, the individuals don't know the type of tree they are in? So my question is, if you know that you are far away from the sources, that there are many sources, it's easier to work out that most of the signals you receive are not true. So can you comment on that, please?
Yeah. So our agents are fully Bayesian and fully cognizant of the shape and the structure of the tree, and they're using all that available information. But when you're in a large tree, even if you know it, then having slight uncertainty about these mutation rates makes it very difficult to figure out what's true and what's false, because most of the things have basically mixed by the time they get to you. And so, I think one lesson from this is in our model, information is not tagged, meaning I don't know how far it has traveled by the time it gets to me. So I hear a rumor that somebody heard something about vaccines, but I don't know what the original source was. And I don't know if it's 20 steps away from me or 3 steps away from me. And so the important part in sort of not being able to sort things out is not knowing what that distance was. So if every piece of information came saying this had only traveled 1 step, or this had traveled 10 steps, it would be a lot easier for me to learn. And so one lesson from this is that actually in these things, if you can tag information in some permanent way where people can't sort of reconstruct their own messages, but you could actually observe the original source and how far it's traveled, the full chain of things, then you could begin to say, look, this thing's come through so many channels, I don't trust what's in this message anymore. Somebody could have corrupted it and put in their own, the not instead of yes, or, climate is not changing instead of it is changing, or, yeah.
Ariel has a question that seems directly related to some of the things you were just saying. Go ahead.
Yeah, I think Matt, hi Matt, I think you just answered my question precisely. So it was exactly about this issue of, you mentioned that WhatsApp, for example, can't keep track of how many hops a message went through, but maybe Facebook can. So my question was exactly, if we could keep track of that and display that information, people may upweight things that traveled few hops and may downweight things that traveled many hops. And as I just said, that could be like another way to address the problem.
Yeah, I think that's exactly right. And I think it's interesting because WhatsApp deliberately encrypts stuff so that you can send whatever you want in messages and they can't peek into it. But then that causes this problem of not being able to tag stuff and making it harder. I think with this kind of system, if somebody's clever, they can always reroute things and make it appear as if it's come from shorter distances. But it becomes more of it's more costly to do. So it's not a complete workaround, but I think tagging information becomes very important. And the more that people can fact check sources and see the distance that things have traveled, the better the learning can be. I think that's sort of an auxiliary part that comes out of the model.
Peter van Emden has a question.
Yes, if it can happen in the network that you're receiving back your own messages after having made a big detour, and you see whether it's mutated or not, can that help you to calibrate these probabilities?
Yeah, I guess I haven't really thought about that. Yes, but so there, if you're looking at cycles where I send messages out, and the more, I think one thing that might be true is that over time we begin to learn more and more about our network. And here in this model, we're assuming that I don't know it might be that certain nodes are ones that distort things from zeros to ones, and other things distort things from ones to zeros. And I don't have enough experience seeing the messages come through that I haven't fully calibrated where those distortions are. And so everything in the model is IID. And it could be that over time, either by my own messages or actually just by repeated observances, I realize that everything that always comes through this one channel is always a one. Then I can begin to, to adjust on that. And so I think, this is sort of looking at a snapshot rather than a repeated learning case where I begin to learn more and more about where the location of mutating nodes are in the tree. And that might come from experience, either from my own messages or repeated interaction with my neighbors, where I begin to learn their biases and who tends to drop things, who tends to mutate things. And that could be very useful, yes.
Jakob Schleuter has a question.
Yeah. So all this discussion has made me kind of curious about, so we've talked about kind of looking at how many times the message has been forwarded or whatever. How would that interplay with cases where someone just like copy pastes a message instead of forwarding it? Would that be seen as just forwarding it, or would that be seen as a, I'll say in kind of air quotes, new message?
Right. So there's a really nice, there's actually a couple of papers by Lada Adamek and teams at Facebook that looked at this kind of mutations, and they have, we reference them in the paper, and the actual mutation rates are alarmingly high. And part of it is because what happens is people will actually take a message and tweak it a little bit when they forward it. So they get a message and then they put in their own little part. So it says, you should support such and you should support such and such at Stanford, they'll add, or they'll add something which actually changes the meaning slightly, and then forward these things. And when you look at those mutations, the mutations build up quite a bit. And in terms of the model, part of that, eventually, if the message is so garbled, you have no idea what it means, that's like dropping a message. I mean, effectively, it just becomes, I don't interpret it as a 0 or 1, that's like a dropped message. But it could also be that I'm sort of, each message I'm trying to put into a bin is, is this in favor of climate change or against climate change? And so the messages come sometimes purely forwarded, sometimes with people's own extra bits to it. And the same thing happens on Twitter. So when people retweet things and add their own message on top, and then you look at the thread, it can be quite, quite difficult to sometimes go all the way back and figure out what the original tweet was, or follow the threads backwards. Okay. So I think different platforms can do different things in terms of the more information you give people and the more difficult you make it to change messages without being obvious about it, the better the learning would be.
Okay, that makes sense.
Stanislav Zhitkov has a question that I think of as a particularly interesting one, because it's the one I'd prepared to ask if there weren't enough questions, but there were plenty of questions.
Yeah, so it seems like under your model, it's already given where the messages originate. And I'm wondering if you considered introducing some kind of adversary, some kind of agent that maybe pays some cost to plant this message at certain nodes. And then the network administrator tries to optimize learning based on where these messages are planted.
Yes, yeah. I think that's a good question, and one that we don't have a lot to say about, because here we sort of take the tree as given, and we're the mutations and so forth as random, which allows us to do the calculations based on the Markov structure. But in general, the game would be very interesting to analyze, and it appears, part of so platforms do try to locate bots and other things that are sending messages deliberately that are disinformation, and those can be hard to locate because sometimes there's organizations that tweet or send messages out as sort of spam-like messages. So like a seminar announcements might look very much like, every once in a while we're getting something and nothing's coming in here, and they're sending out messages repeatedly that are being forwarded by other ones that have similar patterns. So it can be very difficult for administrators to actually spot different types of nodes and identify them cleanly. But I think that's a very important aspect of disinformation, not just misinformation. So I think in our model, misinformation and disinformation are sort of conflated in the sense that we've just got these mutation rates. And it could be that there's deliberate adversaries as opposed to people just getting things confused and sending them along in some noisy manner. And I think both of those are important, and that it would be fascinating to look at this as a game.
Marco Palicia asks, would cycles or links within levels reduce the depth effect?
Yes, so indeed, if things even, you know, so we're looking at trees here, basically the structure and some of the proofs is, you know, Galton-Watson branching processes, and that eliminates cycles, which allows us to track the length of these different paths. But if you can have cycles in the networks, then even in a smaller network, something could take a long circuitous path. You could still try and, you know, limit the relative size of the walks in constructing the network structure. But that's something we haven't looked into, and it would change the actual calculations on the depth and breadth, optimal breadth and depths. Yes, definitely.
Are there other questions? I think Ulla had some words about the next seminar. Ulla, you want to tell us?
Yes, I'm happily going to tell you. So, well, thank you very much for this very nice talk. So next week, we're going to meet again at the usual time, which is 3 hours earlier, with apologies to everyone living west of New York, or at least west of Chicago. I think is tough. And next week will be a special one. It's going to be a rump session, which means there will be 8 speakers, 5 minutes each, with a couple of minutes questions. And it's always a lot of fun. And we have all sorts of things around voting, a little bit of fair division, about preferences, everything you want to have in a proper social choice meeting. So looking forward to it and hope to see many of you there.
Okay. I think that, why don't we give a final round of applause for Matt, since I forgot it the first time. And see all of you, or some of you, next week. Thanks again to the speakers.
Thanks. Bye-bye. See you next week.
Bye.
Thank you. Thanks to the organizers.
Bye.
Bye.
Thank you very much.
Bye-bye.
And Bill, good to see you.
Yes, good to see you.